Good morning friends, and today's topic is complex variables, and this is an exciting area in which we broadly discuss the following topics. Analyticity of functions, in which we will solve some problems based on harmonic functions, the Cauchy-Riemann conditions, the Milne-Thomson method, and orthogonal family of curves. These are the things that we would like to discuss under analyticity of functions. This broadly comes under the concept of complex differentiation. Well, if you first look at harmonic functions, we say a function phi of xy is harmonic if del square phi is equal to 0, that is dou square phi by dou x squared plus dou square phi by dou y square is equal to 0. We will see very soon that all complex analytic functions will have the real and imaginary parts satisfying the Laplace's equation. Then Cauchy-Riemann conditions. Now these are the necessary conditions for a function to be analytic. For example, if you take f of z is equal to u of xy plus iv of xy, if this function is analytic, then the Cauchy-Riemann conditions are true. The Cauchy-Riemann conditions are ux is equal to vy and vx is equal to minus uy. This is in the Cartesian form. When the function is in polar variables r and theta, then these become the Cauchy-Riemann conditions. So we will see a few problems on the Cauchy-Riemann conditions and all that, and related to the same area, there are some terms called harmonic conjugates. That is, when f of z is analytic, then u and v are called the harmonic conjugates of each other. Given u, we can find v. Similarly, given v, we can find u using the Cauchy-Riemann conditions. Then of course, we will be discussing about the Milne-Thomson method, which is used to construct the function f of z. I mean the analytic function f of z when u is given or v is given, or a combination of that. I mean a linear combination like u plus v or u minus v given, we can determine what is f of z. That is where the Milne-Thomson method will be useful. And another concept is about the orthogonal family of curves, in which if f of z is analytic, u and v will be such that they are orthogonal to each other. So based on these four topics, we will have a small exercise now. So let's start the problem sequence. Question number 1. What is the value of b for which the function u is equal to e power bx into cos phi y is harmonic? It is given that u is harmonic. Therefore, uxx plus uyy is equal to 0. ux is equal to b e power bx cos phi y, uxx is equal to b square e power bx cos phi y. Similarly, uy is minus 5 e power bx sin phi y, uyy is equal to minus 25 e power bx cos phi y. So, you take uxx, uyy and substitute in this equation. When you do that, you will find that e power bx cos phi y is a common factor, leaving b square minus 25 is equal to 0. Now, we know e power bx cannot be 0, but assuming that cos phi y is not equal to 0, b square minus 25 is equal to 0, b square is equal to 25, b is plus or minus 5. So, for this set of values, the given function will be harmonic. That means, for this set of values, this will satisfy the Laplace's equation. The correct option for this problem is C. Question number 2. Which of the following functions do not satisfy the Laplace's equation? There are 4 options here. U is equal to log of square root x square plus y squared. Second option, u is equal to tan inverse y by x. Third option, u is equal to 3x cube y plus 2x squared minus y cube minus 2y squared. And D, u is equal to 3xy squared minus x cube. Now, each of these equations may have to be tested for the satisfaction of the Laplace's equation. So, let us start with the first one. Now, we are looking for that option where uxx plus uyy is not equal to 0, because we want that function in the list which does not satisfy the Laplace's equation. So, let us write this as u is equal to half log x square plus y squared. So, ux is equal to half of 2x by x square plus y squared. So, this is x by x square plus y squared. uxx is equal to x squared plus y squared into 1 minus x into 2x by x square plus y squared whole squared. This will give us y square minus x square by x square plus y square whole squared. Now, you can find that u is symmetric in both x and y, therefore, we do not have to recompute uyy. So, uyy can be directly written as x square minus y square by x square plus y square whole square. Now, if you take the sum of these two, you will find that the terms will get cancelled and you get uxx plus uyy is equal to 0. So, this cannot be the correct option because we want that function which does not satisfy the Laplace's equation. So, let us go into the second option and see. In the second option, you are given u is equal to tan inverse y by x. Ux is equal to 1 by 1 plus y by x whole squared into minus y by x squared. This will give us minus y by x square plus y square. When you take uxx, minus y is a constant, differentiate 1 by x square plus y squared, you get minus 1 by x square plus y square whole squared into 2x. So, you get 2xy by x square plus y square whole square. Even though I am not showing you the details, you will find uyy will be minus 2xy by x square plus y square whole square. Again, when you take the sum, you will find that uxx plus uyy is equal to 0. But that is not what we want, because we want that function which does not satisfy the Laplace's equation. So this too is not the correct option. Let us try the third option and see whether we get an answer from there. Now let us try the third option and see whether that does not satisfy Laplace's equation. So ux is equal to 9x square y plus 4x. uxx is equal to 18xy plus 4. Let's take uy. From here you get 3x cube minus 3y squared minus 4y, and uyy minus 6y rather minus 4. So you will find uxx plus uyy is not equal to 0. Therefore, the correct option is option C. So among the 4 functions given to us, it is the third function which does not satisfy the Laplace's equation. However, let us also look at the fourth option, because sometimes you may have multiple correct options. Treating this as ux will be 3y square minus 3x squared. uxx is equal to, this is 0, minus 6x. uy is equal to 6xy. uyy is equal to 6x. So if you take this sum, you will get uxx plus uyy is equal to 0. We don't want that. So this is also not the correct option. That is how we come to the conclusion that only C can be the correct option. So these are problems on Laplace's equation that we can easily understand. Let's go to the next question. Question number 3. This is a fundamental question in analytic functions. What are the Cauchy-Riemann equations in the polar form? We all know the Cauchy-Riemann equations are necessary conditions for a complex function to be analytic. Now, it is customary to write f of z is equal to u of xy plus iv of xy. This is in Cartesian. Since we are in polar, we write this as f of r e power I theta is equal to u of r comma theta plus iv of r comma theta, where r and theta are polar variables. Z is equal to r e power I theta. Now what we do is, we differentiate 1 partially with respect to r in the first case, and differentiate 1 partially with respect to theta in the second case. So let's look at the first thing. F dash r e power I theta into the differentiation of r e power I theta with respect to r will give us e power I theta, and on the right hand side we can write in notation as ur plus ivr. Going to the other side, with respect to theta, f dash r e power I theta into differentiate r e power I theta with respect to theta, and we will get ir e power I theta is equal to u theta plus iv theta. So now we have these two expressions. The easiest way, the basic thing is to eliminate f dash. So we simply divide. So divide, let us say this is second equation, this is third. Suppose you divide third equation with the second equation. So then you will be left with IR is equal to U theta plus IV theta divided by UR plus IVR. We will cross multiply IR UR minus RVR, because that's I square is equal to minus 1 U theta plus IV theta. So we have got a complex quantity on the left side and a complex quantity on the right hand side. When two complex quantities are equal, their real imaginary parts must be equal. So you can equate these two real parts, you can equate these two imaginary parts. From here you will get minus R VR is equal to U theta, which implies VR is equal to minus 1 by R U theta, and by equating the imaginary parts you will have R UR is equal to V theta. Therefore, UR is equal to 1 by R V theta. So these two equations, UR is equal to 1 by R V theta and VR is equal to minus 1 by R U theta, are together called the CR equations in polar form, and this you can find in option A. Question number 4. If f of u comma v is equal to u plus iv is analytic, then what is the harmonic conjugate of v of x comma y is equal to e power x into sin y? So we are given f of z is equal to u plus iv is analytic. As explained earlier, if the function is analytic, u and v are harmonic conjugates of each other, which means because v is given, we must now find out what is u. There are two options for this. One is to come to the Cauchy-Riemann equations and the other is to come to the Milne-Thomson method. Let me explain the Milne-Thomson method of solving this problem. The formula to determine f of z, given the imaginary part v is this. That means you will also have another Milne-Thomson formula when u is given. Okay, what we do is we differentiate v with respect to x and y partially and then replace x with z and y with 0. So let us see what is dou v by dou x. This will be e power x sin y itself. Vx at z comma 0 is e power z sin 0, so that will be 0. Similarly, Vy is equal to e power x cos y. So Vy at z comma 0 is e power z cos 0, so this will be e power z. So if you apply this into this one, f of z will be dou v by dou y will be e power z plus I into v of Vx at z comma 0 is 0. So I into 0 dz plus constant. So this is nothing but the integration of e power z, which is e power z plus constant. Replace z with x plus iy. So when you do this, you will get e power x into e power iy is cos y plus I sin y. So you can clearly see that e power x sin y, which is v, is appearing in the answer. So this will form the u part of the function, and therefore this is the harmonic conjugate of that. Therefore, the harmonic conjugate of v of xy is u of xy is equal to e power x cos y, which you can find as option C in the list. Some students may feel this is slightly longish, but you can also come through the Cauchy-Riemann conditions. This apparently looks long, but it's very, very easy if you know the separation technique very well. So let's go to the next question. Question number 5. If f of z is equal to u plus iv is analytic, then what is the output of dou square by dou x squared plus dou square by dou y squared of real part of f of z whole squared? So given f of z is analytic, let us say f of z is u plus iv. Because it's analytic, ux is equal to vy, vx is equal to minus uy, and also equally important is that both of the real and imaginary parts satisfy Laplace's equation. That means they are harmonic. So what we are trying to say is these 4 conditions may be kept ready in case we will have to use them. Because the function is analytic, generally 4 conditions are available. So let's take this calculation. We can write this as summation over xy dou square by dou x squared. Real f of z is nothing but u. So it is u squared. So this is nothing but summation over xy dou by dou x of 2u dou u by dou x. So this is nothing but twice summation over xy u into uxx plus ux squared. That is by using the UV rule. So when you unfold this summation, you will get 2 more similar terms in terms of y. So you will get 2 times u times uxx plus uyy plus ux squared plus uy squared. But you can use this information at this stage. Uxx plus uyy will be 0, and you can replace uy with minus vx. So let's simplify this part. 2 times 0 plus ux square plus minus vx square. So this will be 2 times ux square plus vx square. You can write this as 2 times mod f dash z whole squared. This is because when f of z is equal to u plus iv, f dash z can be written as ux plus ivx. So the modulus of this will be square root of ux square plus vx squared. So you can see that ux square plus vx square can be written as the square of mod f dash z. So therefore, this is the output of the problem, and you can find that this is available in option B. In fact, this is a very famous result which students generally directly remember instead of having to work it out. But in case you forget to remember, then it will not take much time to do this. But every time a function is analytic, please keep in mind that these 4 conditions may be kept ready for application. So let's go to the next question. Question number 6. What is the analytic function f of z is equal to u plus iv whose real part is u of xy is equal to e power minus x into x sin y minus y cos y? This is a direct application of the Milne-Thomson formula. So for your reference, f of z is given by integral of ux at z comma 0 minus iuy z comma 0 dz plus constant. So the procedure is there to be understood. Find ux and uy and evaluate both of them at z comma 0 and put it into the integral formula. So this is the Milne-Thomson formula to construct f of z given u. So let us see ux. You have to be careful because there is a product rule of differentiation. With this as fixed, differentiate this with respect to x and you will get sin y plus x sin y minus y cos y to derivative of e power minus x is minus e power minus x. Without wasting time on simplification, let us evaluate this at z comma 0. And you will find when y is 0, this is 0, this is 0, this is 0, and you will get minus e power minus z. But this will vanish completely. So in the integration, there is no contribution of this term. Let's take uy. Now e power minus x is a constant. Differentiate with respect to y. You get x cos y plus y sin y minus cos y. Again, evaluate at z comma 0. You will get e power minus z. When x is z and y is 0, this becomes z plus 0 minus 1. So this is z minus 1 e power minus z. So you take this and substitute into that formula. So you will find f of z is equal to minus I integral z minus 1 e power minus z dz plus of course some constant. You have to only integrate this by parts. You get minus I into z minus 1 into minus e power minus z minus of 1 into e power minus z plus constant. So this will be minus I into minus z e power minus z, and of course plus e power minus z minus e power minus z will get cancelled, and you will get iz e power minus z plus constant. So this is the required analytic function given the real part through the Milne-Thomson formula, and you will find the correct option for this problem is D. Question number 7. What is the analytic function f of z is equal to u plus iv, where the imaginary part v of xy is equal to y cube minus 3x square y plus c? So we apply the Milne-Thomson formula. F of z is equal to integral vy z comma 0 plus I into vx z comma 0 dz plus constant. So let's start with vx, and you'll find that is minus 6xy, from which we can write vx at z comma 0 will be 0, x is z, y is 0. Vy is equal to 3y square minus 3x squared, which means Vy at z comma 0 will be 0 minus 3z squared, that is minus 3z squared. So if you now apply it into the Milne's formula, f of z is equal to integral minus 3z squared plus I into 0 dz plus constant. So this is nothing but minus z cube plus constant. Of course, this constant can be a real constant or imaginary constant, and you will find that in the option 1 the constant is coming along with the imaginary I. So if you let c is equal to some ki, f of z is equal to minus z cube plus ki matches with one of the options. So you can find option D matches with this one. So in practice, the c can be real or imaginary, or it can be a complex number of the form a plus ib. So this problem was selected to show you how the imaginary part can help you to find out the analytic function f of z. As I told you, students also prefer not touching the Milnod's formula but directly going through the Cauchy-Riemann equations. But I feel for a quick results this equation can be remembered. Let's go to the next question. Question number 8. What are the orthogonal trajectories of the family of curves x cube y minus xy cube is equal to constant? We can do this problem using complex variable theory. Let us take this as a real part of an unknown analytic function f of z. F of z is u plus iv, and we discussed earlier that the real and imaginary parts are mutually orthogonal provided the function is analytic. So we can build the function and then extract v out of that, for which we can apply the Milnod's formula given the real part. So the goal is to find v. Those will be orthogonal to the trajectories u. So let's begin with ux. 3x square y minus y cube. Therefore, ux at z comma 0 will be 0 minus 0, which is 0. Uy is equal to x cube minus 3xy squared. So uy at z comma 0 will be z cube. So if you now substitute ux and uy into the Milnod's formula, f of z will be integral of minus iz cube dz plus constant. So when you integrate this, you get minus I z power 4 by 4, of course plus constant. So this is minus I by 4 into x plus iy to the power of 4. You can give a binomial expansion here. So minus I by 4 into x power 4 plus 4x cube into iy plus 6x squared into iy whole squared plus 4x into iy whole cube plus iy to the power of 4 plus constant. Now what we are looking for is the imaginary part. Already minus I is here, therefore we must select these terms. If you select these terms, because they come along with I, will constitute the v part. So let us see what is v of xy. This is equal to minus I by 4 into x power 4 minus 6x square y squared. Of course, this I should not be written, plus y to the power of 4 plus constant. So you can find that minus 1 by 4 into x power 4 plus y power 4 minus 6 x squared y squared plus c is the final output. So it is these curves which will be orthogonal to the given family of curves, and we will find that this is available in option A. So finding the orthogonal trajectories in analytic functions means finding out the harmonic conjugate itself. So when you finally analyze, it is only around CR conditions, harmonic conditions and Cauchy-Riemann equations which will dominate the topic on analytic functions. Let's go to the next question. Question number 9. What is the harmonic conjugate of the function u of r comma theta is equal to minus r cube sine 3 theta? This is a problem related to analytic functions involving polar coordinates. So when you have f of z is equal to u of r comma theta plus iv of r comma theta, if this is analytic, then the Cauchy-Riemann equations will be ur is equal to 1 by r v theta, Vr is equal to minus 1 by r u theta. U is given, we have to find out what is V. So the goal is to find V. So let's find out Ur. This is minus 3r square sine 3 theta. So ur is equal to 1 by r v theta. So this is equal to 1 by r v theta. Therefore, v theta is equal to minus 3r cube sine 3 theta. So if you want to find out v from here, you have to integrate the right hand side partially with respect to theta. So you will get 3r cube cos 3 theta by 3 plus constant. So v is equal to r cube cos 3 theta plus constant, which of course you can also derive by taking the second Cauchy-Riemann equation. Of course, for that you must find out u theta first, then equate it, find out Vr is equal to minus 1 by r u theta, and then find out V by integrating partially with respect to r. Any of the two equations can be used. So ultimately the result will be the same. So you will find that option A for this problem is the correct option. So with these illustrations, the concept of analyticity of functions can be understood and practiced. So let's go to the next topic, which is on complex integration.